let's see. Okay. Let's, I guess, get started. Okay, so this is the second class of CSE 547, the discrete mathematics. Let's start off with, first of all, any questions about logistical matters or technical matters. Are there any questions? Okay. The latest development, okay, is that we now have a new TA. You people wore out the old TA, okay, since the first class, okay, and so we have a new TA. The details will appear on the web page, but let me just sort of zoom in here. Why don't you come on up, okay? His name is Hui. Come on up to the stage so we can get you on tape, okay? Hui Z. Okay, I guess, how do you pronounce it?
Xie.
Okay, sorry about that. Sorry. Okay, let's try this again. First name.
Hui.
Hui. Second.
Call me Huey.
Huey. Is that okay, or?
Okay.
Okay, Hui or Huey. Okay, Z. Okay. His room number is 1208. Okay, he believes his phone number is 632-7678. Okay, his email, of course, is different. What is your email?
XHUI.
XHUI at CS.
Yeah, okay.
He's going to try to keep the same office hours, but check on the website for that to make sure that that's correct. Okay? So let's give a big round of applause to Nute, big enough that we keep him for a while. Okay, let's take a look. Very good. Okay, thanks a lot, and we'll see you then. Okay, any other questions or administrative matters before we begin? Okay, any questions one way or another? Okay, last class we started talking about, okay, yep, so let's zoom this down. Last class we started talking about summations. Where do we got this thing? Hold on. Hold on. There we go. Okay, last class we started talking about summations, okay, and recurrence relations. We're talking basically about recurrence relations. This class we're going to start talking a little bit more about summations, okay? Summations are a very important kind of combinatorial formula to deal with, okay, that we'll see actually are intimately related with recurrence relations, okay? You should all be familiar with the sigma notation. The sigma notation, okay, an expression something like this, I equals 1 to n of ai, is basically saying, give me the sum, sigma is sum, of the terms a1, a2, ... up to an. Okay? Sometimes you see it written like this. Sometimes you see it written like this, where both the upper and lower indices are written within some kind of constraint. So this says that I is between 1 and n. Okay, and it means for all I between 1 and n. Okay, this is the same thing as that. The important thing to see about the summation notation is that it's a notation. Okay, a notation is something designed to help you understand things. The reason we have a sigma instead of writing everything out like that is because it's a clearer way to write things. Okay, and if we take a look at the notation, though, the sigma notation by itself can actually be still confusing way to express sums, or tricky way to express sums. And so one of the things that most of you have seen sums and summations in one form or another. Okay, you've probably solved some simple summations. One of the things that the book is going to try to teach you, and that I think is a useful thing, okay, during our brief exposure to sums, we'll spend about a week on it, okay, is the idea of looking at a somewhat different notation for representing sums that may be easier to work with. Okay, one of the things that you have to do fairly often when you're writing a sum is to express exactly what you want to sum over. Okay, and a summation symbol like this is fairly easy to deal with. It's also uncommon to have to do a sum something like this, like the sum of all squares of odd numbers between a particular bound. Okay, so one way that you could represent the summation, here we want to now sum as I goes from 1 to anything less than 100, which means from 1 to 99. Take all the values of that are odd, which I guess means 1, 3, 5, ... up to 99. For each one of those, square them, okay, and take the sum of that. Now, normally, when you want to represent that, okay, or when I've been used to representing sums, usually the way that you would proceed is you take a look at something like this and try to rewrite it so as to get rid of this term k odd. What does k odd mean? Okay? And usually what you would end up trying to do is some kind of a substitution of the form. Well, if you want to make an odd number is 2 times something plus 1 or minus 1. This is a way to guarantee you an odd number. Okay? By rewriting k as 2k plus 1 and limiting the axes so that, let's say, we don't, limiting the bounds on the summation. So here, if you think about it, there's 99 possible numbers. Half of them are going to be odd. So if we reduce the upper bound on our summation by a half and count every other term, by doing some kind of a summation like that, okay, by doing those kind of manipulations, you can express a summation with a funny constraint like that as a straightforward kind of sum that you may be used to dealing with. Okay? Any questions about the moves that it took to go from a sum written like this to a sum written like that? Any questions or comments about how you see it? Now, so you should be comfortable with the idea of making these kind of substitutions. The one thing that I will warn you about, okay, is that these are often dangerous things to do. They tend to be error-prone kind of substitutions. They tend to be tricky for the same reason that writing programs tend to be tricky, or one of the reasons is sort of boundary conditions. How do you know whether to start from 0 and go to 49? We could have written this maybe instead going from 1 to 50. Okay? How do we know this was a plus 1 and not a minus 1? And so on. So, one of the things that this book does is it tries to introduce a different notation for manipulating sums, okay, which, if you get comfortable with working with, can maybe make it easier to try to reason about things than doing these substitutions too quickly. Let you maybe see what some of the structure or tricks that you might see. And introducing a summation is an important thing, okay, and the way I like to illustrate it is to think a little bit about the story of calculus. Who here knows who invented calculus? Okay, who was the inventor of calculus? Yes. Isaac Newton is one person who invented calculus. Anybody else know who invented calculus? Okay, yeah. Leibniz. Okay, the second guy is Leibniz. Okay. Now, what is the story? Isaac Newton is the one that's all famous for inventing calculus. Okay. Well, what was the story? Basically, Leibniz and Newton invented calculus about the same time. You know, Leibniz in Germany, Newton in England. Okay. Now, England's mathematicians were very powerful, and Newton was a famous guy. And they immediately set to work to discredit Leibniz. Okay, so Leibniz didn't invent it, Leibniz stole it. Okay, and as far as the British mathematicians were concerned, the story basically ended happily. Newton became famous, Leibniz died a broken man buried in an unmarked grave. Okay, but who had the last laugh? Okay, well, it wasn't Leibniz, but in some sense it was. Okay, the notation that Newton used for calculus, okay, was a very cumbersome notation. And all the British mathematicians felt obligated to use Newton's notation because, you know, Newton was British and all this kind of stuff. The notation that Leibniz used is basically what is the forefather of the notation that we now use. And for the next couple hundred years, while the British mathematicians were stuck using Newton's notation, the mathematicians in France and Germany were able to advance the theory of calculus because they had a better notation to work with. So notation can be a very important thing. And like I say, one of the interesting things is in this book, Knuth introduces sort of a new notation for dealing with sums. What is that notation? That notation is based on, if you want to think of it, it's, you can think of it as based on either the Kronecker delta function that you saw in calculus or a programming predicate that sort of existed in APL. Suppose we have a function. We think that every time we have a function, you know, stuck in parentheses, we'll say this is a point function. Okay, p prime, okay, is going to be a function that is going to be 1 if p is prime and 0 if p is not. Okay, So this is sort of like the delta function you would have seen in calculus, where again you have sort of the notation n equals k. This means that this is a function that is going to be 0 everywhere except at a. Okay? And there it's going to be equal to 1. Why is this a useful thing? A couple of reasons. Okay? The main reason is it gives us the option of sticking logical terms into expressions and manipulating them. Okay? So let's think of an expression something like this, where you have the sum as of 1 over p, as p for all p less than or equal to n, okay, where p is prime. I claim a way that you could write this expression using the sort of, we'll call this thing the Iversonian notation, would be that we assume we've got like a Boolean predicate here that is going to be 0 if p is not prime and 1 if p is prime, and another one that is 0 if p is not less than or equal to n, and 1 if it is otherwise. And we're now going to sum over all integers p. Okay, summation by definition happens over the integers. Okay, because we're dealing with discrete math and not reals. Okay, so it's something that happens over the integers. What do we read this expression as? Well, if we think about it, if this is under the condition that either this is not true or this is not true, what does that term contribute to the sum? Okay, I claim it contributes 0 because 0 times anything is 0. Okay, so we can use this to wipe out certain cases. Okay, like the fact that since 0 is not prime, okay, it wipes out the term that might have 1 over 0. Okay, so it gives us a way to talk about these things. And we can now talk about reasoning about these logical terms the way they are as logical terms. At some point, we'll have to get rid of the logical terms to get them down to something we understand, perhaps, okay, or can manipulate. But the advantage of this notation is maybe we carry it along in a way that makes things transparent longer. Okay? Any questions about the notation or why we might want to do it this way? Okay? Good. Question? Why would you want to do it this way? The major reason I claim is that a lot of the conversions, as I mentioned before, a lot of the conversions, okay, that you would use to get rid of these logical conditions tend to be fraught with error. And the longer you can push them off and think about them, the better off you likely are to be. Okay? The other thing is that somehow that once you've made a substitution like this, you've lost the fact you're no longer thinking about even and odd numbers. Okay? And that may or may not be, later on you may see some kind of cancellation where you can think at a higher level. Okay? If you like the notation, use it. If you don't like the notation, don't use it. Okay? Knuth and Graham are top-notch discrete mathematicians, and they like the notation. Okay? And I like the notation.
But
Question?
How would you solve the same thing? Suppose you can certainly solve this summation.
So the question is, how do you go about doing the summations? We'll look at some examples over the next couple of classes. Okay? And to a certain extent, at some point, you may very well need to go back and do substitutions. Okay? The question is, just as a way of writing it cleaner, it's, first of all, having a long list of conditions tacked on underneath a summation sign is not a particularly cumbersome, easy thing to work with. Okay? And the goal is maybe you can find ways to simplify it later. Okay? Again, conceptually, a notation buys you nothing. Okay? There's nothing you can't do with this notation that you could do with the other notation and vice versa. Okay? But it's a different way of thinking about it that may be a useful thing. Any other questions? Okay, good. So let's look at not so much, it's not really a particular use of that notation, but let's look at some examples of, last class we talked about solving recurrence relations. Okay, we showed an example of solving a recurrence relation. I claim that summations are very, very closely related to recurrence relations. Why? Suppose we have a summation of the form here. We have S sub n is going to be equal to the first n terms of A, this is the series A. I think that we could equivalently write it as some recurrence of the form S sub 0 equals A sub 0. And then S sub n equals S sub n minus 1 plus A sub n. Why is this equivalent? Well, if A sub n is the sum of the first n minus 1 terms, n minus 1 terms plus the nth term is going to give us the sum of all n terms. So it should be clear that this is an alternate way to write it. Okay? And so if you were very good at solving recurrences, you in principle solve summations. Okay? Any questions about that? That should be kind of obvious. What it buys you now may or may not be obvious. Okay? But let's look now at solving a particular general form of a summation, okay, by using a recurrence. Okay? And this is going to introduce us to a method called the Repertory Method, which I think is a useful way of thinking about summations. Suppose, let's say, we now want to solve, okay, compute the sum of, okay, or let's go back to here. Let's say we want to compute the sum of a series A sub n, all terms A sub I as I goes from 1 to n, where A sub I is B beta plus gamma n. So beta is some kind of a constant, gamma is a constant, n is our iteration variable. I claim we can express that summation, okay, as of the form R0, the 0th value of our recurrence is alpha, the initial value. R sub n equals R sub n minus 1 plus the value of the nth term, which we said was B plus beta plus gamma n. Okay? Now let's look at a way of solving this recurrence, which we really agree is just a summation, okay, using something called the Repertory Method. Okay, any questions at this point? Okay? What is the idea of the Repertory Method? Okay? The Repertory Method is as follows. Okay? If we can convince ourselves that the solution of our recurrence, okay, is of a particular form, okay, namely, suppose we can convince ourselves that the solution of our recurrence is some function times alpha, the first constant, plus some function times beta, which is the second constant, plus some function times the third constant, which is gamma. My claim is that if we can find independent solutions to our recurrence relation, okay, for three different functions, okay, for three different sets of constants, then I claim we can go and figure out what those functions have to be by working backwards. Okay? Any questions so far? Okay, this may not be clear. Let's look at an example. The first thing that I'd say if I were trying to solve a mysterious sum might be to go to construct an example. Okay, what is it actually, the value of this recurrence? My claim is, if I were to sit down and, this is not in the notes, okay, this is something I just made, a little extracurricular thing, okay? But basically, if I just built up the table, for n equals 0, R sub n is alpha. For n equals 1, R sub n is going to be B beta plus gamma times 1 plus alpha, or A alpha plus beta plus gamma, and so on. You can build this sort of table of what the possible solutions are. Okay? Once you have that, it may be you can start to think about guessing a solution. And there's sort of two different ways to work this kind of guesses. Okay? The most obvious one might be to try to guess what the values of the function associated with each one of these three constants is. Okay? So does anyone want to guess if we have a solution of the form R sub n is alpha n times A sub n times alpha plus B sub n times beta plus C sub n times gamma? What is alpha n, or A sub n? Does anyone want to suggest what that function is from looking at this data? Okay, the function is probably 1. Okay, that seems pretty obvious. Okay? What is the function associated with B sub n? N. Okay? What is the function associated with C sub n? Okay? Now here, okay, it shouldn't be quite so obvious. Okay? Looking at this, I mean, I happen to know the answer. Okay, and so you can say it's obvious if you know the answer. Okay? But what we've got now is a situation where if we could have guessed what all three of those functions were, okay, we would then know what the answer is, and then maybe we could prove it by induction. Okay? One problem is here we now have a complicated function that we can't guess the answer to. Okay, or maybe you could beat on it and try to guess the answer. The repertory method is going to be some way that's going to try to figure out a way to get these three functions. Not by guessing the functions individually, okay, not by guessing an, bn, cn, but by guessing different values of the recurrence. Okay? Any questions so far? So what is our example here? Let's take a look at this thing. Suppose we have, okay, a recurrence relation of the form, again, Rn is equal to, basically the same recurrence relation we had there. What I'm going to want us to do now is to find three different linearly independent sets of the constants, okay, A, alpha, beta, and gamma, such that they will generate different solutions for the recurrence relation. Okay? Now we're going to work backwards. Instead of looking at what the values of the functions times this are directly, let's look for special cases of this recurrence we can know how to solve. And so we're going to look for two different things. We want sets of constants such that we can solve them, and yet such that they do yield different solutions. Okay? Can anybody yield, let's take a look at this recurrence relation. R0 is alpha plus Rn equals beta plus beta equals that plus gamma equals that. Can anybody give me values of alpha, beta, and gamma such that you do know how to solve that problem? Okay, that you could, if I gave you what values of these constants would make it easy for you to solve them. Okay? The 1, 0, 0. Why does 1, 0, 0 make that easy? Well, if you make it 1, 0, 0, you've got a recurrence of the form, okay, R0 equals 1, Rn equals Rn minus 1. That means you're defining the function Rn equals 1. Okay? So you now have a set of constants such that you know the solution, R1. Okay? Any questions about that? Okay? We now have a way of setting these constants to yield us a solution. Okay? Can we set constants to yield some other solution? Now, the easiest way to get a different solution, we just set, let's say maybe A1 alpha equals 2. Okay? And leave the others as 0. But that doesn't yield a significantly different solution. Okay? It's linearly just sort of, it's a constant times that. They're not linearly independent. Can anybody think of a way of monkeying with these constants, okay, so as to yield a different solution? Okay? Any ideas? Okay? I claim that by monkeying with the constants, I could get the function R sub n equals n, okay, fairly easily. How could I do that? Well, if R sub n equals n is a solution, then the way I could figure it out what constants to take to get that, okay, is by sort of back and back substituting. We know that if R sub n equals n, what does alpha have to be for R sub 0 to be 0? Well, alpha's got to be 0. Now we know that R1, okay, meaning 1, okay, is going to be equal to 0 plus beta plus gamma. We have that equation. And if we want R sub 2 to be equal to 2, then that's going to have to be 1 for Rn plus beta plus n times gamma, where n is 2. You've now got two equations and two unknowns. By substituting them, you can find out constants to generate the following recurrence relation. Okay? And I think now you'll agree that R sub n equals R sub n minus 1 plus 1 is in fact and obviously a recurrence such that R sub n equals n. It's a recurrence that counts. Okay? So nobody should be too surprised. This recurrence generates that. Okay? Any questions? Now we've got one other type of function. We had three constants and two functions. If we could now find a third function, a third possible solution, that's different. Let's now go through it and do so. What might be reasonable guesses for what that third function is? Okay? Maybe it's 2 to the n. Maybe it's some constant to the n. Or maybe it's n squared. Okay? I claim that if you happen to guess the function n squared, okay, which is again not an unreasonable, again you're playing around with it, it's not an unreasonable thing, by going through and doing the same kind of substitutions we did before, okay, you could find the 3 values of the constants to yield a recurrence such that r sub n equals n squared. Okay? So you take the first 3 values of n, you know what n squared is going to be. It's going to be 0 squared, 1 squared, and 4 squared. Once you set those constants, you've got a recurrence relation. Just because this recurrence relation happens to match n squared for the first 3 terms doesn't by itself mean that this recurrence relation magically happens to realize n squared. You could certainly, let's say we were talking about Skinner's function, which was n squared up to 100, and then became 0, okay? Maybe it'd be the value of Yahoo stock after a crash or something like that, okay? You need to then prove that this recurrence relation is, in fact, n squared, but that can be done by induction, okay? How can you prove that this is equal to induction? Well, the basic, again, it should be a fairly simple proof. You assume it's true to some point. Then you back substitute. If r sub n minus 1 is, in fact, if this recurrence does in fact yield n squared, then r sub n minus 1 is n minus 1 squared. N minus 1 squared plus 2n minus 1, if you work that out, in fact, is n squared. So that's a proof that we found the right way to set these constants. Okay? And if we've set those constants, now what do we have? We have 3 distinct solutions. We have 3 distinct constants. Okay? And I claim that now we can solve the system of equations, okay, so as to yield what a sub n, b sub n, and c sub n have to be. Okay? We have, again, the situation we've got here is, going back to the original thing, we've convinced ourselves that r sub n is going to be of the form some constant times some function n, some constant times some function, some constant times some function. We have 3 different sets of constants, each of which yield different functions. By now solving for a sub n, b sub n, and c sub n, okay, that gives us a solution. Okay? And I claim this gives us a reasonably general and reasonably powerful way to solve recurrences. Okay? Any questions about that? Okay? Any questions one way or another? Question? So the question is now, how do you calculate a(n), b(n), and c(n)? What I claim is, it's easy to calculate. The first thing is to calculate alpha, beta, and gamma. These are the constants that generate this recurrence. Now let's go through and see what is it that we actually know, okay? What is it that we actually know? We know from our first case, if I were to go back and, let's see, where did we have this thing here? What is it that the first case tells us? The first case tells us that sub n, that setting alpha equals 1, okay, and beta equals, and gamma equal to 0, yields the function 1. So that tells me that 1 is equal to what? It's equal to a sub n times 1 plus b sub n times 0 plus c sub n times 0. What does the second case tell us? Everybody agree that that's what it tells us? What does the second case tell us? The second case tells us that n is equal to, okay, what? Okay, n is going to be equal to, if I take a look at this thing, sorry if it's a little confusing now, maybe I'll put it like this. It tells us that n is going to be true, alpha is going to be 0, so that's going to be the same as 0 times a sub n plus 1 times b sub n plus 0 times c sub n. Okay? And the final example tells us what? The final example tells us that n squared is going to be equal to, if I set the constants right, alpha equals 0, okay, which means 0 times a sub n, plus b sub n times what? Minus 1, plus c sub n, which was equal to 2 times that. My claim is I now have 3 sets of equations, okay? Solving these for a, b, and alpha and beta and gamma will in fact yield the solution, okay? Any questions about how you do that? How many people would like to see me do that? Okay? A couple of people, okay? Well, what I first claim is that since all these are zeros, ka-chunk, ka-chunk, we've just proven that a sub n has to be equal to 1, correct? If we go back up to there. Is this visible? Yes, it is. Okay. Over here, what does this tell us? These are zeros and these are zeros. Ka-chunk, ka-chunk. So b sub n is going to have to be n, correct? Now, if we go back and substitute, what does this tell us? This tells us that n squared is going to be equal to 0 plus minus n plus 2 times cn. Okay? And solving for cn, what does that tell us? That tells us that cn is going to be equal to n squared plus n over 2. Okay? And so lo and behold, that's exactly what I claim to get over here, which is not always going to happen, I think, this semester. Okay? But lo and behold, what the answer has to be. Okay? And so this gives us a general recurrence now for all values of those constants. Any questions about how we did that? Okay? I urge you to think about it, and I urge you to take a look. There's another example of the repertory method a few pages earlier in the lecture notes, and as well as in the textbook, so you may want to think about it that way. Okay? And again, to see how powerful the solution is, notice that this gives us another way of computing the sum of the first n integers. Okay? Namely, the sum of the integers from 1 to n. Because if we set the constants appropriately, we get that special case. Namely, we'll get if we set beta equals, anyway, I claim that if we set the constants appropriately, okay, to generate the recurrence relation, you have to set those constants based on the recurrence relation. If you do that, that will end up yielding the solution alpha and beta equals 0, alpha 1, beta equal to this. It ends up yielding the solution that you want. Okay? Any questions? Okay, good. So I urge you to think about that and see how it goes. Another technique. Okay, so that now gives us a way now, I claim, gives us a way of trying to guess solutions to things. Okay, and work through it. Okay? As we saw there were 2 different ways to guess. We could have looked at the data and guessed what the individual functions were, or look at the recurrences and see what kind of solutions we could get out of it. Okay? Both of which would lead things to solutions. This notion of recurrence relations and summations are very intimately related. Okay? In fact, we showed before how you can convert any sum to a history 1 recurrence relation. Okay? In fact, the conversion can go the other way. You can convert any history 1 recurrence relation to a summation. Okay, so these 2 things really are the same kind of thing. Okay? What do I mean by history 1? History 1 basically means that t sub n depends only on t sub n minus 1. The history of a recurrence relation is the difference between the left-hand term and the smallest index on the right-hand term. Okay? So, how can you convert any history 1 recurrence to a history, to a summation? Well, look at the following trick just to see what I mean by that. Suppose we have the recurrence relation t sub 0 equals 0, t sub n equals 2 times t sub n minus 1 plus 1. Okay? If we want to sit down and think what does that actually sum out to, it should be pretty easy to solve this recurrence relation, I think, in your head. Okay? Writing down some examples. But let's look at a slick trick. Let's convert it to a summation. One thing that's true is notice that if we divide both sides by t to the n, 2 to the n, 1 over 2 to the n, what happens? If we divide both sides by 2 to the n in this case, 2 to the 0 is what? Okay? 2 to the 0 is 1. So I claim that dividing both sides of this recurrence by 1 leaves things unchecked. Everyone will agree that t sub 0 over 2 to the 0 is certainly still equal to 0. Correct? What happens in general if we now divide both sides of the recurrence, in general, by 2 to the n? Okay? Now what we've got is t sub n over 2n to the n equals t sub n minus 1 over 2 to the n minus 1 plus 1 over 2 to the n. Where does the t sub n minus 1 come from? Well, here we had a 2. It canceled one of the 2 to the n's. What happens if we've got here? Well, if you look at this thing, there's actually, it looks like almost a recursive kind of thing. Here we have t sub n over 2 to the n, t sub n minus 1 over 2 to the n minus 1. If we perform the substitution, s sub n equals t sub n over 2 to the n, what actually happens? Well, now I claim, by doing that substitution, what we really get here is s sub n, okay, is going to be equal to t sub n over 2 to the n. S sub n minus 1 is going to be equal to t sub n minus 1 over 2 to the n minus 1. I claim that the equivalence of this original recurrence sum, okay, recurrence, is the recurrence s sub n equals s sub n minus 1 plus 1 over 2 to the n. And this, if you look at it, is because you've got coefficient of 1 and a coefficient of 1 here. This recurrence can be expressed by a simple summation, namely the sum of, as I goes from 1 to n, of 1 over 2 to the I, or equivalently 2 to the I minus 1. Okay? Any questions at this point? Okay? What should be clear if you look at it? It should be clear that we have succeeded, okay, in reducing this particular recurrence relation into this particular recurrence relation. This particular recurrence relation is clearly a sum. It's a sum of a geometric series, okay, if you want to think of it that way. And in fact, this recurrence relation happens to have a fairly obvious answer, okay? If you take a look at it, it's, what is it, the sum of 1/2 plus 1/4 plus ... This, I claim, is, just based upon laws from summing geometric series, this is going to be 1 minus 1/2 to the n. Okay? So this thing is now a sum that's been solved. Where does that leave us? Well, we know that t sub n, if s sub n equals t sub n divided by 2 to the n, t sub n then is going to be equal to 2 to the n times s sub n. If s sub n is in fact equal to 1 minus 1/2 to the n times 2 to the n, well, 2 to the n times 1 is 2 to the n. 1/2 to the n times 2 to the n is 1. In fact, this gives us a way to solve that summation. It's going to be equal to 2 to the n minus 1. Question. Move it up. Okay? Yes, when my slides are not visible, you may want to shout out if I'm not looking, because I may get on a roll here. Okay, and not hear you. Okay? So what have we just done? I claim that I've just shown you how we solve this recurrence relation by reducing it to a summation. Okay? The trick was that we did a substitution. Okay? And how, the thing that may not be clear if you pore over this and think about it a little bit. All of this I claim is reasonably straightforward, modulo this magic substitution. Okay? How did you see, okay, that you substitute S sub n equals T sub n over 2 to the n, and that suddenly things happen? Okay? What I claim is that there is a general technique for solving these kinds of recurrence relations. Okay? Okay? That there's a general way to find that substitution. Okay? Provided the recurrence that you have is of the form, okay, some function a sub n times t sub n equals some function b sub n times t sub n minus 1 plus some other function. Certainly the example we have here was, if I go back and take a look at that, was certainly of that type, because here we had a sub n equals 1, b sub n equals 2, and c sub n equals n. Okay? Any questions of where we're sitting or anything like that? Okay? Let me just show you how you can actually do the substitutions. Okay? Unless there's any questions. So let's think, how could we sort of solve a recurrence or convert a recurrence to a summation where the recurrence is of the form, okay, that we had stated? Okay? Well, suppose, let's say, I have a function, S sub n, which is defined by the property S sub n times b sub n equals S sub n minus 1 times a sub n minus 1. What are we trying to do? Well, again, here was the recurrence you gave me. It was of this form, a sub n times t sub n, b sub n times t sub n minus 1 plus c sub n. Suppose I now have this function s sub n, which is defined by this property. It has the fact that s sub n, there is an s sub n that is defined by this property. What happens if I multiply both sides by that? Well, this is going to be S sub n times this, plus S sub n times that, plus S sub n times that. That's fine. Here we've got S sub n, A sub n. Here we've got S sub n, B sub n. Well, S sub n, B sub n, by definition, is equal to S sub n, okay, minus 1, A sub n minus 1. If we do that substitution, now we've got a recurrence that looks like this. Okay, where here everything that we've got is an S sub n, is n as a subscript. Everything here we have is so it has sort of n minus 1 as a subscript. That means we can now go about doing, okay, the substitution big S sub n is defined as S sub n, A sub n, T sub n. If we do that, we now have that big S sub n is equal to big S sub n minus 1 plus little s sub n times c sub n. Okay? This is a summation. Okay? Because this clearly is a summation. The question still remains, how do we go and find what that little s sub n is? We had this definition here of what was useful. If S sub n observed that, if we had an S sub n with this property, then we could do the substitution we had in mind. That's clear. What is that little S sub n? Well, we know by definition that S sub n equals S sub n times B sub n is going to be equal to S sub n minus 1 times A sub n minus 1. What do we know about S sub n minus 1? Well, by definition, it's going to be equal to, okay, S sub n minus 2 times A sub n minus 2, B sub n minus 2. We could keep substituting this thing all the way down until there's basically nothing left. We hit the endpoint condition. Okay? And my claim is once we've done that, what we're going to get is that S sub n is going to be the product of the first n minus 1 terms of A divided by the second, if you want to think of it, n terms of B. Okay? And you've got your terminating condition there. So if you remember that from T sub n, in the original case, okay, we had magically guessed that S sub n was a solution of the form 1 over n minus 1. Well, how did we get that? Well, if you take a look at this thing, A sub n was always going to be equal to 1. That was the thing. If we go back and zoom it away. A sub n was the thing before the first term, so A sub n was 1. B sub n was the coefficient of the second term. B sub n was always 2. This tells me there are 1 to the nth over 2 to the n minus 1. And 1 to the n minus 1 over 2 to the n minus 1. That's where the 1 over 2n minus 1 comes from. Okay? Any questions? I realize there's a lot of algebra here. People get lost in algebra. Okay? But I urge you to go through and think about this. Okay? Go through, work it out until you feel comfortable with it. Okay? This provides you a way of converting back and forth between recurrences and summations. Any questions about that? One way. Any questions? Okay. Let me think about this. Let's look at an example of this technique, okay, applied to a very, very famous recurrence relation which comes up in computer science that you've probably seen a couple times before in algorithms classes. This is the recurrence relation associated with the sorting algorithm Quicksort. What is the sorting algorithm? Well, basically it picked at random some element in, let's say you want to sort an array of n elements. Suppose you picked at random one of the elements in that recurrence relation, in one of the array, okay? That'll be our pivot. We then sweep through the entire array, okay, filling the elements, picking the element, go to the left of it and to the right of it. Once we do that, all the elements less than the pivot will lie to the left of it. All the elements greater than the pivot will lie to the right of it. Okay? And so depending upon which element we picked, okay, the element we picked for our pivot was picked at random. It's equally likely to lie at any one of the n positions in sorted order. Okay? Once we have picked that that pivot, okay, suppose it lies in the kth position, okay, or the k-less first position. Okay? My claim is that divides the sorting problem into two parts, one of which is consists of the first k elements, one of which consists of the last n minus k element. The pivot element itself is in the right position. Okay? Any questions about how Quicksort works? This should be probably seen before. Okay? Well, let's analyze what is the expected number of comparisons done. The expected number of comparisons done against a pivot as we go through this thing. Well, how many comparisons are going to be done in quick sorting something that has 0 elements in it? Okay? Well, I think it's fair to say 0 is a reasonable basis case for that situation. In general, what are we going to actually pay? My claim is that with equal likelihood, we're going to pick a pivot k, okay, as lying anywhere between the 0th and nth position. Okay? Again, we have to make sure we get the between the first and nth position, or equivalently the 0th to n minus first position. Okay? You have to make sure you get your indices right. Okay? We're going to have to pay a cost for partitioning in comparison to cost and partitionings for partitioning the array. Okay? That would actually happen regardless of which pivot element you pick. To compare all the elements in it, you pay a cost of this for doing the partitioning. The interesting part of it is how much do you spend on the next level? Okay? After you've done some partitioning and broken it into pieces of size k and size n minus k, my claim is you have to still now quick sort recursively an instance of size k and an instance of size n minus k. So the cost of our recurrence, the rate recurrence, is the partitioning cost plus, with equal likelihood, one of each of the following n cases. So that's why we divide by n. We break it where the pivot element was chosen to be in the kth position. Any questions about the recurrence? Okay. The bigger question is now, how do you solve it? Okay. And this recurrence, if you look at it, there's a couple of this is not an easy recurrence to solve. Okay, if you haven't seen it before. Okay. One move should be pretty easy, is to notice that here you've got a sum that's going from k goes from 0 to n minus 1. Here you have a sum that's going from, as k is 0, n minus 1 down to 0. You've got two instances here of the same sum. You're just summing them up in a different order. My claim is that you could replace this by, for that reason, 2 instead of 1, and get this down to one instance of the recursion. Okay? Any questions about that? That should be easy. Okay? Any questions? What is the history of this recurrence, by the way? How big is the history of this recurrence? Is this a history 1 recurrence? No, because it goes all the way back to n. This recurrence has about as much history as you can, and certainly about as much history as any recurrence in computer science. Okay, I think that's a fair statement there. Okay? So we can't directly apply the tricks that we did before. Okay? The next step, though I claim to reduce this to a history 1 recurrence, is a general way of getting rid of sums. What if we multiply each side by n? We get a recurrence that looks like this. We've now got n times c sub n plus this. We've now got a history recurrence here. Suppose we subtract the same value of this. We want to get rid of this sum here. The sum is sort of an ugly thing to deal with. Okay? If we subtract that sum, okay, notice that this recurrence is defined for all values of n. Here we've got some constant times a summation on n terms. If we subtract this for a smaller value, for the recurrence instantiated for n minus 1, what's going to happen? Well, this is going to go from n to n minus 1. This goes to n minus 1, n minus 1, n minus 1. And the interesting thing is the only thing that changes here is the index. So what happens when we subtract the sum of something as it goes to n minus 1 minus the sum of things as it goes up to n minus 2? What's left? Okay? The clever thing about this summation is, and this trick of taking the thing and subtracting it from its previous value, is that it wipes out this internal summation. Okay? And that what gets left here is these two terms agree on everything except the n minus first term. When we subtract it, we've got this minus this. Well, n minus 1 times cn, there's no corresponding term, we get that. Here we've got, there's no corresponding term to the cn minus 1, we've got that. Here, these things are polynomials, those get mashed around. And the important thing is the sum goes away. So the big trick that's a useful one to see, that's not an obvious one, but something you should be aware of, is this trick that the best way to get rid of a deep history in a recurrence is often to subtract a smaller, consider instantiating the recurrence for one smaller, or some constant times one smaller, and then wipe out the terms. Any questions about that trick? Okay. You'll see a lot of tricks in here, some of which you won't be able to use. This is one you will be able to use. Okay. Once you've got that, we now rearrange the terms. Okay. And now we've got a recurrence of the form c sub n times c sub n is equal to n plus 1 times c sub n minus 1 plus 2n c sub n. Now we have a history 1 recurrence. Okay? And lo and behold, we have a history 1 recurrence of exactly the same type that we had before. Okay? Namely, we've got some function times this, some function times that, okay, and some function here. If you do that, then that means that there exists something we can multiply both sides by, some function s sub n, such that we can reduce this thing to a special case. Here the substitution was s sub n. Actually, okay, then I claim that there is some way you can do the substitution. Okay, because this is the exact same format as before. How do you go about doing it? Well, in this particular case, again, there's lots of different ways maybe you can go about it subtly. But basically, in this case, if you now multiply both sides by 2 over n plus 1, namely to try to get rid of, to try to make it more like a recursive R type, the n is going to cancel, the n plus 1 is going to cancel. We've now got a recurrence that's of the form n over n plus 1, n minus 1 over n plus something. You can almost see the history forming by doing a substitution of the form s sub n. Okay, a new recurrence equals the old recurrence c sub n plus n minus 1 over n minus 1. We now get a simple summation. Okay, because now we get s sub n equals s sub n plus 1 over 2 to the n, 2 over n, plus 2 over n plus 1. Okay, this is in fact the sum of, as I goes from 1 to n, of 2 times 1 over k plus 1. Pull out the 2, you've got a simple thing here. Okay? Any questions about this? I realize what I just did was probably very boring. Okay? Any questions? But what's the interesting take-home lesson? The interesting take-home lessons are, first of all, how did we kill the summation? Okay? That's a take-home lesson. Once we had a form of this type, you knew that there was a way to do it if you go back to Knuth. Okay? Look at the notes, look at Knuth. The other take-home lesson that's important is, in fact, the form that the equation we finally get at the end is. Okay? In the end, we're getting something of the form. The sum as k goes from 1 to n of 1 over k plus 1, okay, 1 over k plus 1. This is not that much different by changing the summation. Namely, this is the sum, if you want to think of it as the sum as k goes from 2 to n plus 1 of 1 over k. That would be an equivalent way of writing this statement. The value of 1 over 1 is pretty simple. That's 1. If you take this sum is very closely related to a sum of the form, the sum of the numbers 1 over I as I goes from 1 to n. This is a sequence of numbers, okay, that one sees over and over and over again. Okay? It's important to sort of recognize when one sees that type of number. Okay? We define the harmonic numbers, h sub n, as being equal to, where h sub n is the sum of the first 1 over I, the first n simple fractions, i.e., the sum as I goes from 1 to n of 1 over I. That's what the nth harmonic number is. This summation will come up over and over again. You have to recognize it. It is your friend. Okay? The important thing to others see about it is that by working on it, you're not going to be able to simplify that straight ahead. When you see a term like that, the best thing is to say, hey, that is the definition of the harmonic numbers. Okay? And leaving it in that form is fine. Especially because it's well known that the value of the nth harmonic number is approximately log n, the natural log of n. Okay? I believe it's within 1 of the natural log of n. Okay? So leaving it in this form is perfectly fine. Okay? And putting all those facts together, now we see why Quicksort is an n log n algorithm. Why? Because ultimately we've got that c sub n, the number of comparisons for the nth term, is going to be equal to n plus 1 times s sub n. S sub n is going to be, okay, 2 times the, basically the nth harmonic number. The nth harmonic number is log n. That gives us something like 2 times log n times n. That's why we have an n log n algorithm for Quicksort. Any questions about where we are here? Okay, good. Now, when we're working with sums, there really are, if you want to think of it, only three basic tricks, not tricks, basic manipulations we're legally allowed. Okay? And all of these are fairly simple and fairly obvious. Okay? We know that when we have a summation, and we have something multiplied by the term that doesn't depend upon the index, we can pull that thing that doesn't depend upon the index out of the recurrence, out of the summation. So a constant times a sub n, okay, is, we can make the same as putting c times, that c can go outside the summation. Okay, that's really an application of the distributive law. Note that this is not necessarily true just for constants. Okay? We could have this function, suppose this thing was a function z squared. Here we have an index k, z squared might be some other variable. So long as z does not depend on k, we can pull that thing out. Okay? That's the idea of the distributive law. The associative law says that you can rearrange terms, associated with a summation. So this is often used to break apart summation. Suppose you have the sum of two things within an expression which is in the form of something plus something else. We can break that into two simpler sums. The sum of all the first terms plus the sum of all the second terms. If you can solve each one of these separately, they're then easy to combine again at the end. Okay? Or, the other thing we can do is rearrange the terms, because addition is commutative. So if you have an index, a summation that goes as k, all k, as k is counting maybe from 1 to n. If we rearrange the order of the summations, that should leave the sum unchanged. So we can apply an arbitrary permutation to the indexes of the sum here, provided we also manipulate the indices within the term. Okay? This is the sort of substitution you make when, let's say, like in the previous, we did something of this type in the quicksort recurrence. Okay? When we combine the two sums. If you want to look at this thing, basically here, we had a sum that was going, if you wanted to think of it, here we had a sum that was going from 0 to n. Here we had a sum that was going from n minus 1, 0 to n minus 1. Here we went from n minus 1 to 0. By changing the indices, we rearranged these terms. These had the same set of terms. We rearranged them and combined them. Okay, and that was the trick. Okay? Any questions? So in dealing with sums, again, it's a tricky business, because basically the ability to solve sums is the idea of applying these rules in the right order. And the thing that's tricky about it is you don't really know necessarily what the right order is until you're done. Okay? So there's a certain amount of going back and forth you must be willing to do with a sum. Okay? Sometimes you can think about it as being some kind of a tree you're building of substitutions in solving a sum. One path through that tree will give you the answer. Okay? Hopefully, aesthetically, by trying to simplify things, you find that path. But if not, you got to go back and try again. Any questions about that? Okay. Yes, question.
Earlier, when you show how to get rid of the summation sign.
Right.
How do you actually do that? You just, because you made one summation sign more than the other?
Okay, so how did we actually do that? The question was, how do we get rid of the summations in the quicksort recurrence? Okay. Again, I encourage people asking questions. Okay, so let's go through this thing one more time. What was the trick? We have a recurrence of the form something times the recursive value is equal to something plus the sum of a bunch of recursive terms. Okay? This made it a history in recurrence. History n recurrences are ugly. Okay, we want to get rid of that. Okay, that's a good general practice. How do we get rid of history n term? If you think about it, the best way to get rid of it is to somehow subtract away all the values, okay, as many of the values of this recurrence as possible. Okay, try to subtract out what that sum is. So we'd like to find some way to find a representation for the sum of the terms from 0 to n minus 2. If we have something like this, something else equal to it, by subtracting this thing, we will cancel all but that last term. Okay? What is the strategy for seeing that? The key strategy for seeing that is to see that when we instantiate this recurrence with a different value of n, we will in fact get it with some constant here. Okay, this is going to become from n, if we instantiate with n minus 1, this will become n minus 1 minus 1, or n minus 2. Okay? That was the key observation that we had here. Let's look at another example, just flying a little bit blind here. What if I give you a recurrence of the form, let's just call it, we'll call it u sub n for an ugly, u sub n meaning ugly. What if we have here something of the form n times, okay, the sigma as I goes from 1 to n minus 1 of u sub I. Okay, this is a little bit uglier than what we saw before. Why is this uglier than we saw before? Because it's got the same history as before, but in fact, the difference is that we have a constant. Okay, instead of having a constant, okay, to worry about, we have a general variable here. Okay, suppose let's say it was a constant. Let's say 42, the universal constant. Okay? If I now want to put in what is u sub n minus 1, u sub n minus 1 is going to be defined as 42 times the sum as I goes from 1 of n minus 1 minus 1, n minus 2 of u sub I. What is this minus this? This would give me u sub n equals u sub n minus 1 equals 42 times what? The only thing that's left is u sub n minus 1. If we had that, we've got u sub n equals minus u sub n minus 1, u sub n minus u sub n minus 1 equals 42 u sub n minus 1. We can bring this over there to say that u sub n equals 43 u sub n minus 1. And we're done. Okay? So by doing the deletion trick, this instantiated by its history trick, okay, we got rid of that. Okay? Any questions about that? But let's look at a more general case of this, because this is kind of an interesting thing. Suppose, let's say, I gave you the recurrence, as the general one I had given you, u sub n equals n times u sub n minus 1. Okay? How is it going to be worked? How could we get rid of that? Suppose we instantiate the other thing. Okay, what would that be? That would be u sub n minus 1 is equal to n minus 1 u sub n minus 1. Okay? Actually, oh wait, excuse me, we had a summation here. Let's go back here. U sub n was equal to the sum as I goes from 1 to n times u sub I. If we want to get rid of that sum, suppose we just used u sub n minus 1. That would be n minus 1 times the sum as I goes from 1 to n minus 1 of u sub I. If we subtract that, does it help us? Okay? If we subtract this thing, do we end up canceling all the terms? And the answer, I say, is no. Why not? Okay? Well, because the problem is that now we're going to have n times, okay, u sub n, n times u sub n minus 1 Here we've got n sub I. When we subtract this thing, we're going to end up with getting sum as I goes from 1 to n minus 1 of u sub I. Here we have n times it, n minus 1 times it. The subtraction doesn't do the trick. Okay? How many people see what I mean by the subtraction not trick? Raise your hands locally so I know. Okay, good. How do we solve the problem? Okay? Question. Answer. So we could apply the same method, but if you see it intuitively, what you want to do is to somehow make these things common. Okay? You need to multiply this thing by something that will get rid of that. Okay? What is the thing that we can multiply both sides by to get rid of that thing? Suppose we multiply it by n times n over n minus 1. Okay? And this by n over n minus 1. Now what we're going to have here is a sum n times this. Here we're going to have, when this cancels, n times that. Okay? Now we've got the same coefficients, and all that's going to get left is the last n term. Okay? This basically is the trick that we were applying before. Okay? And it shows how we hack that sum down to size. Any questions about it? Okay? Think about it. Again, my handwriting is not very good when I do it spontaneously. That you probably will figure out. Okay? So that's why I try to use the the prepared notes as much as possible. Okay. What else can we do quickly? Okay? What I want to claim is there's two special classes of sums, okay, that you should know how to solve, okay, because they are important sums, okay? First of all, there are arithmetic progressions, okay? Namely, this is what we were working with so far, okay? This is a sum of the form some constant plus some constant times the index, perhaps plus some constant times that index squared or something like that. If you've got a sum of the form, summing up as I goes from some index to another index, of some polynomial in that index here, that kind of expression can always be solved. Okay, that's sort of the important thing to see. Okay, that for arithmetic progressions such as this, the sum, we have, for example, here we have the sum of, this is basically the sum we've been working on. These sums can always be solved. Okay, and that's an important thing to keep in your bag of tricks. Okay, those we call arithmetic expressions. We've seen how to solve this a couple times. I don't want to go through with it because we're a little short on time. The other type of summation that you'll see all the time, okay, is geometric progressions. So here what we've got is something where we've got a sum S sub n is going to be the sum of, as k goes from 0 to n, meaning the index, the exponent of our sum is changing. Okay? That's what we mean by a geometric progression. So here S sub n equals the sum as k goes from 0 to n of a times x to the n for some value of x. Okay? It should be pretty clear you could factor out the a here. That's not interesting. Okay? But the difference here is that, here we've got, instead of a sum of polynomials, here we have an exponent. The exponent itself is what's in the summation. Okay? The index is in the exponent. If we have an expression like that, these are in fact a type of summation that in fact it's well known how to solve. Okay? You've probably saw this back in high school. Okay? How can we solve it? Well, let's look at the following trick. S sub n is defined as being the sum of the first n terms of this series. Let's look at what happens when we take the first n plus 1 terms of that series. Okay? The first n plus 1 terms of that series is the sum of the first n terms plus a times x to the n plus 1. That's pretty obvious. Another way to write that thing is to go to take a look at the sum as I goes from 0 to n plus 1. Okay? Pull out the 0th term. Here we have implicitly n plus 1 terms. N plus the largest one. Here we can rewrite it as the lowest one plus the n other terms. The interesting thing is, if you look very carefully at this summation, here we've got essentially the same term as before, except that here the exponent's higher. Okay, here there's n terms if you go and rewrite the indices. Here you could rewrite this thing as being a sum with the same over the same indices of x to the n plus 1. This was going to be x sub 0 plus x sub 1, 2, 3 up to n minus 1. This was going to be x to the 0, 1, 2, 3 up to the n plus n minus 1. Once we have it like this, the interesting thing is that we could pull out one of the x's from that exponent, namely reduce that k plus 1 to x times the sum of this to the k. That, by definition, is s sub n. We end up with an expression s sub n plus a sub x to the n plus 1 is equal to a plus x sub n. Solving for x sub n, you end up with the following expression, which is a very, very useful summation, something you've probably seen in high school. Okay? This has the expression as being the one that I probably tend to look up in a book more often than any other one. I can never remember this formula, but I know it exists. Okay? It tells me that the sum of a geometric terms has a closed form. And so whenever I've got something to that expression, then everything can be solved, and it's just cookbook from there. Okay? Any questions about how I did that summation? What trick I used to do that? Okay, what's the punchline? Okay? Again, solving summations is somewhat of an art. Okay? What are the general rules? Okay? Again, how useful they are depends. Okay? But basically, again, whenever you have a summation index, pull out what you can. In general, don't cancel zero terms too quickly. Okay? One thing that people sometimes do is they'll change indices. They'll see a summation of the form where it goes from 0, the summation maybe goes from 0 to n. And they'll say, well, I can subtract out the 0th term and then change my indices. It's not clear that factoring out zeros may end up creating, you may have a summation, leave yourself with a summation form 3, going from 3 to n. And that may be a harder thing to see patterns with. Okay, so in general, I don't try to cancel zero terms too quick. Again, think about what special cases you know how to solve. You should know about harmonic numbers. You should know about geometric series. You should know about arithmetic progressions. These kind of things you should say, once you see them, you say, boom, that's cookbook, and I'll do it. Okay? And finally, when you've got messy stuff, okay, like summations in summations, okay, or recurrences and stuff like that, see if we can do some kind of some substitution to cancel it or get rid of it so that it's just sort of one simple variable and deal with it from there. Again, to apply these things takes practice, but that's why you got homework. Okay? So get going on the homework, okay, and start practicing. Any questions beforehand? If not, thanks for your attention. See you guys next class. Okay.